Okay, hello. I will present work that mainly is in a paper that I presented at AIMC 2024 last year with Stefano Fasciani, but I will contextualize in the context of my broader PhD research. So the project is about autonomous control of synthesis parameters with listening-based reinforcement learning. And it comes from the idea of music improvisation and wanting to make agents that can improvise music according to some criteria. And specifically, I focus on non-idiomatic improvisation, also called free improvisation, which is basically untied from a macrostructural musical context. And we want more to explore timbre relationships, dynamics, and so on. And I define improvisation as making decisions in time. So it means that the musicians and the autonomous agents in this case can make decisions according to an environmental context. I start with the idea of an autonomous agent, which is described as a system that inhabits a dynamic and predictable environment with a set of time-dependent goals. And we can think of an autonomous agent as being composed of a sensor, an effector or actuator, and some kind of algorithm that connects the sensor to a response in the environment. And in this case, musical agents, we can think of them as artificial agents that automate some kind of musical creative task. And in doing so, they effectively make aesthetic decisions as part of a performance. And these have been described as live algorithms. When the sensor is some kind of sound analysis, the effector is some kind of synthesizer, and the patterning reasoning component is what determines the musical response. So we have some person emitting some sound, some analysis, some reasoning, some synthesis, and a response that the person hears. And what I was interested in is this aspect here, the reasoning part. And for this reason, I got interested in reinforcement learning as a way to model this as a control problem for a black box synthesizer in such a way that we can define musical objective and choose our own synthesizer to train the agent to control it, just based on sound. So this is the kind of model of a improvisational interaction. We have a person controlling some instrument with some kind of control actions, and then listening back and interacting with another person that's controlling a different instrument through, again, like sensing, listening, processing, and action. And in this case, we want to substitute this with an agent, with a machine, and controlling a digital synthesizer through some kind of sensing, so understanding musical listening, patterning, reasoning, and then controlling. And then we want to control this system through some kind of method controls. And then here the problem becomes defining what we want the system to do. And this is the main topic of this research project. So short introduction to reinforcement learning. It's an unsupervised machine learning technique in which an agent is in an environment. The agent can act on the environment through some action and then modify the state of the environment through the action. And it learns through simulation in the environment, and it basically judges which actions have been successful, have modified the state of the environment successfully according to some reward function, which in this case will we decide what it is, and it's based on some kind of musical objective that performer might have. So when this translates to a live musical interaction problem, we can think of a live musician playing at each time step t, playing some instruments, the agent playing a digital synthesizer, and we extract features from this, from both of them. And together with the parameters of the synthesizer controlled by the agent, they form the state of the environment, so what the agent is listening to. And then the agent can act on the environment through some changes in the synthesis parameters. And this will affect, of course, the synthesis parameters and the features extracted by the synthesizer, but at the same time, the musician will be playing something different. So this is can be defined as a reinforcement learning with dynamic environment, because the agent doesn't have, in this case, a model of the environment. It builds the model of the environment through training, through kind of trying to predict what this feature extraction from the musician will be. And in this case, we experimented with a discrete action space, which means that the changes in the parameters can only be of some step at each time step. So for example, we can move each parameter value down or up or keep it the same. And then we modify this according to some step size. This is also possible to change it in a continuous action space, but it's easier to test it like this. And for our first experiment, we decided this was the best way to go. The way this is trained is through a musician corpus, a small corpus of 2 or 3 recordings, can be even more, of 2-3 minutes each. That is, features are extracted through the corpus, and basically we have a bunch of strategies to facilitate this this process. But what happens is that at each training episode, a step corresponds to 1 frame of, I think it's 1024 samples. And so we have, the agent can act at each frame. And 1 episode of training is 1 track from the training corpus. And at the same time, since in this experiment we didn't want to synthesize sound during training because this would take a lot of time, we made a lookup table basically mapping combination of synthesis parameters to the extracted features. And the kind of, I think, most interesting part of this is the reward function, which can be really adapted to different musical objectives. In this case, we wanted to try timbre matching, and this kind of works. So basically the reward function is dependent on the similarities between the 2 feature vectors. So it's the weighted root mean square error between the 2 feature vectors, and we can also have this B vector, which allows us to select only a subset of the feature vectors. So for example, if we want to use the information from all of these descriptors as a state of the environment, but then train only matching, for example, loudness and spectral centroid, we can do that. And this also determines the musical objective of what we want to do. And then now I'm experimenting with differences. Yes, we can go into this later if you're interested. Some reward tweaking to make everything converge, and some some inspiration of what other possible reward function could be based on this. Yeah, we can talk about this later. Now it's a small demo of the system with a few different synthesizers. This is mono, so it don't mind. Yeah, I'm playing with the controller of the synth. To match the sound dynamically. Yeah, so just some discussion points. I think this technique is still not really usable in performance because it's kind of not very reliable, and it needs more investigation to make it more dynamic. But it shows that it's the reinforcement learning model works, and yeah, and it's adaptable to several synthesizers, several different sound sources, but it can be expanded in many ways. We could include a memory, a larger memory in the reward function to look at larger time windows in the past. Multi-scale also it can be done, and yeah, continuous state space and more knowledge of the environment. Yeah, so thank you, and this is the code is here, and yeah,